take a moment. You can last without food for a good stretch, maybe even a bit without water, but try holding your breath. It really hits home how utterly vital the air around us is, this unseen sea we're constantly swimming in. And here's something for you to wrap your head around. 99% of everything that makes up our atmosphere is crammed into just the first 32 kilometers above us. That incredibly thin layer is all that stands between us and the vacuum of space. And, well, within it is the very essence of life. Oxygen for us, carbon dioxide for plants.
It's fascinating, isn't it, how something so fundamental often just, fades into the background of our awareness.
Exactly. So for this deep dive, we're going to pull back the curtain and explore precisely what makes up this atmosphere and how it's structured, drawing from some really interesting material we've looked at.
Yeah, and our aim really is to equip you with a clear and insightful understanding of the atmosphere's components and its layered structure. And perhaps more importantly, to reveal why each of these aspects holds significance for our planet. We'll distill the essential information for you.
Okay, great. So with that fundamental importance in mind, let's really get into the nitty-gritty. What exactly makes up this atmospheric blanket? We call it air, but what are the actual ingredients? And does that recipe change as we go higher up?
Excellent questions. At its core, the atmosphere is, well, a blend of various gases that envelops the Earth, held in place by gravity. It's worth noting that this gaseous envelope isn't just a passive shell, it's actually an integral part of Earth's overall mass. Now, while gases are the dominant components, we also find varying amounts of water vapor and tiny particles suspended within it. And yes, to answer your question, the proportions of these elements definitely shift as you ascend. For example, the oxygen we depend on so heavily down here at ground level becomes virtually undetectable above, say, 120 kilometers. Similarly, carbon dioxide and water vapor are largely concentrated in the lower 90 kilometers or so.
Huh. That's a bit of a surprise. I kind of pictured the air being a much more consistent mix all the way up. So, okay, let's zero in on some of these specific gases. Carbon dioxide is constantly in the news. What's its crucial role beyond just being, a byproduct of our breathing?
Right. Carbon dioxide, even though it makes up a relatively small fraction of the total atmospheric gases, plays a disproportionately large role in our planet's meteorology. It's really quite key. What's particularly interesting is how it interacts with energy from the sun. It's transparent to incoming solar radiation. Basically, it lets sunlight pass through to reach and warm the Earth's surface. However, it acts quite differently with the heat that the Earth radiates back out. It's largely opaque to this outgoing terrestrial radiation. This means it absorbs a significant portion of this escaping heat and re-radiates some of it back towards the surface. This vital process is, of course, the greenhouse effect, and it's what keeps our planet at a habitable temperature. Without it, we'd be frozen.
Right. It acts like a thermal layer, trapping some heat.
Mhm.
But we also hear a lot about the dangers of too much carbon dioxide.
Precisely. While the greenhouse effect is a natural and necessary phenomenon, the extensive burning of fossil fuels since the Industrial Revolution has led to a substantial increase in the concentration of carbon dioxide in the atmosphere. And because it traps more of the Earth's outgoing heat, this increase is directly linked to the observed rise in global temperatures. That's the central concern in, the context of climate change.
Okay, yeah, that's a clear picture.
Yeah.
Now let's talk about ozone. The ozone layer, that's something we all know is important, but maybe not exactly why or where.
The ozone layer is another critical component, primarily situated in the stratosphere, which is roughly between 10 and 50 kilometers above the Earth's surface. Its primary and really essential function is to act as a natural shield. It absorbs the vast majority of harmful ultraviolet UV radiation emitted by the sun. By filtering out these intense UV rays before they reach the ground, the ozone layer is absolutely indispensable for protecting life on Earth. Without it, we would face, dramatically increased risks of skin cancer, damage to plant life, disruptions to entire ecosystems. It's vital.
So it's our planet's built-in sunblock, basically, high up in the atmosphere.
Okay, what about water vapor? We all know how much humidity can affect how the air feels.
Water vapor. It's unique because its presence in the atmosphere is highly variable. It depends significantly on both geographical location and altitude. In warm, humid tropical regions, for instance, it can constitute as much as 4% of the air by volume, whereas in dry, cold desert and polar areas, it might be less than 1%. And generally, its concentration also decreases as you move upwards.
Okay.
Similar to carbon dioxide, water vapor also plays a significant role in absorbing both incoming solar radiation, that's insolation, and outgoing terrestrial heat. Think of it as another layer in our atmospheric blanket, helping to moderate Earth's temperature and prevent extreme swings between day and night, for example.
Hmm.
Furthermore, the amount of water vapor present dramatically influences the stability or instability of the atmosphere, which in turn drives our weather patterns. It's key for weather. Interesting. So even though it fluctuates a lot, it's still a really important player in the whole atmospheric system. Now, the last component you mentioned was dust particles. I have to admit, I don't usually think of dust as a key part of the air. Seems like
Yeah.
just dirt.
Well, dust particles, while often invisible to the naked eye, are indeed a crucial component. They're not just dirt. They originate from a wide array of sources. Think sea salt crystals carried by winds from the oceans, fine soil particles eroded from land, smoke and soot from fires in industry, pollen from plants, and even tiny fragments of meteors that burn up way up high in the atmosphere.
Wow, okay.
While their concentration is generally highest in the lower atmospheric layers, strong upward air currents convection can lift them to considerable altitudes. You often find a higher abundance of these particles in subtropical and temperate regions compared to the more humid equatorial and polar zones, largely due to the prevalence of drier winds there.
Okay, so they're constantly floating around up there, these tiny specks from all sorts of places. But what do they actually do? What's their function?
Right. Here's where it gets really interesting, actually. These minuscule dust and salt particles act as what we call hygroscopic nuclei.
Hygroscopic nuclei.
Yeah, basically they provide tiny surfaces in the air around which water vapor can condense. Water vapor needs something to condense onto. This process of water vapor turning into liquid water droplets is the very first and essential step in the formation of clouds.
No way.
Yes. So without these microscopic particles suspended in the atmosphere, we wouldn't have clouds. And consequently, no rain or snow. It's a foundational element of our planet's water cycle.
That's incredible. I honestly never connected something as seemingly insignificant as, well, dust to something as fundamental as rain and clouds. Okay, so now we have a much better understanding of what the atmosphere is made of, the gases, the vapor, the particles. How is it actually structured? I know there are different layers.
Yes, absolutely. The atmosphere isn't just a uniform blob of air extending into space. Its density and temperature change significantly with altitude, and these changes are what allow us to divide it into 5 distinct layers. It's important to remember that the density of the atmosphere is highest near the Earth's surface. That's gravity pulling the air molecules down, and it gradually becomes thinner or less dense as you move upwards. These layers are primarily defined based on how temperature changes with height. That's the key differentiator.
Makes sense. So what are these layers, starting from the ground level where we are?
Okay, the lowermost layer, the one we inhabit and crucially where all our weather unfolds, is the troposphere. On average, it extends up to about 13 kilometers. However, its thickness varies quite a bit. It's thinner near the poles, maybe around 8 kilometers, and thicker at the equator, reaching about 18 kilometers.
Why the difference?
It's largely due to the strong convectional currents driven by the intense solar heating at the equator. Think of it like heating a pot of water. The heat rises more vigorously in the middle, pushing the surface higher. So the intense solar heating at the equator drives more powerful upward air movements, puffing up the troposphere there.
Got it.
And as we've discussed, the troposphere contains the majority of the atmosphere's dust particles and water vapor. Crucially, all the phenomena we associate with weather and climate, rain, wind, storms, clouds occur within this layer. This makes it absolutely vital for all biological activity on our planet. A key characteristic of the troposphere is that temperature generally decreases with altitude. It gets colder as you go up at a fairly consistent rate of about 1 degree Celsius for every 165 meters you ascend.
Right, the lapse rate. It's why mountaintops are colder than valleys.
Yeah.
That makes intuitive sense. So what's the layer directly above the troposphere?
Separating the troposphere from the next layer up is a transitional zone called the tropopause. Pause like it's pausing the temperature drought. In this region, the temperature generally stops decreasing with height and becomes relatively constant, or even starts to slightly increase in some conditions. Interestingly, the temperature at the tropopause varies significantly between the equator, where it's incredibly cold, around -80 degrees Celsius.
-80?
And the poles, where it's warmer, relatively speaking, about -45 degrees Celsius. This temperature situation at the tropopause acts sort of like a lid, preventing significant mixing between the troposphere below and the stratosphere above. It has major implications for weather patterns and how things like pollutants get distributed.
Okay, so it's like a frigid boundary layer. And above that is the stratosphere, right? That's where you said the ozone layer is.
Precisely. The stratosphere extends from the tropopause upwards to about 50 kilometers. And as you mentioned, its most significant feature is the presence of the ozone layer. Now, within the stratosphere, the temperature actually starts to increase with altitude. It gets warmer as you go higher through this layer.
Oh, the opposite of the troposphere.
Exactly. And this is because the ozone layer absorbs the sun's UV radiation, converting that energy into heat. So this absorption is what shields us from harmful radiation, but it also inherently warms this layer of the atmosphere, creating that temperature increase.
Got it. So temperature goes down in the troposphere, then starts going back up in the stratosphere because of the ozone doing its vital job. What comes after the stratosphere?
Above the stratosphere, extending from about 50 up to 80 kilometers, is the mesosphere. Meso meaning middle. In this layer, the temperature trend reverses again. It begins to decrease with altitude, reaching the coldest temperatures in the entire atmosphere around minus 100 degrees Celsius at its upper boundary, which we call the mesopause.
Minus 100. Colder than the tropopause even. So it's like a really cold filling in the sandwich between the warmer stratosphere below and what's above, the thermosphere.
Correct. The thermosphere lies above the mesopause, extending from about 80 kilometers way up to around 400 kilometers, though boundaries are fuzzy up there. Within the thermosphere is a fascinating region called the Ionosphere. It's not technically a separate layer, more like an electrified region within the thermosphere. It's characterized by the presence of ions electrically charged particles. This ionization happens because the sun's high-energy radiation knocks electrons off atoms and molecules up there.
And that affects radio waves, right?
Exactly. A very important function of the ionosphere is that it reflects certain frequencies of radio waves back to Earth. This phenomenon is crucial for long-distance radio communication. Ham radio operators love it. Now, unlike the mesosphere, temperature in the thermosphere increases significantly with altitude again. It can get extremely hot, technically speaking.
Hot, even though the air is thin.
Yeah, it's a bit counterintuitive. The air density is incredibly low. The molecules are very far apart. So while the individual molecules are moving very fast, which means high temperature, there aren't many of them. You wouldn't feel hot in the traditional sense. You'd freeze because there's so little matter to transfer heat to you.
Oh.
But this is also the layer where you see the mesmerizing Aurora Borealis, the Northern Lights, and the Aurora Australis, the Southern Lights.
Oh, no.
These spectacular light shows happen when charged particles streaming from the sun, the solar wind, collide with oxygen and nitrogen atoms in the ionosphere, causing them to get excited and emit light.
The Northern Lights, it's amazing to think that's happening way, way up in that incredibly thin, electrically charged layer. And finally, the very outermost layer. What's that called?
The uppermost layer is the exosphere, exo meaning outer. It lies above the thermosphere. There's no sharp upper boundary. The extremely rarefied gases, very, very thin air in the exosphere, gradually thin out further and eventually just merge with the vacuum of outer space. Due to its extreme remoteness and low density, our knowledge about the exosphere is relatively limited compared to the lower layers we've discussed. But we understand it's kind of the fringe, where some lighter gases like hydrogen and helium can actually escape Earth's gravitational pull entirely.
So it's like the atmosphere just sort of gently fades away into space up there. That's a really fascinating structure, layer by layer. Earlier, you mentioned that geographers are particularly interested in certain layers. Which ones hold the most significance for them, and why focus there?
Yes, that's right. While all layers play a role in the Earth's overall system, geographers tend to be primarily concerned with the troposphere and the stratosphere. The troposphere is obviously key because it's where all our weather and climate phenomena originate and unfold. It directly influences human activities, ecosystems, agriculture, everything at the surface. And the stratosphere, with its crucial ozone layer, is also vitally important because it regulates the amount of harmful UV radiation reaching the surface. This has profound implications for both environmental health and human health.
Okay, that makes perfect sense, given geography's focus on the Earth's surface and its inhabitants, and the processes directly affecting them. So we've explored what the atmosphere is made of, the gases, vapor, dust, and how it's layered from the ground up. Now, shifting our focus slightly for the last part, the outline mentions elements of weather and climate. What exactly are these fundamental elements?
Good transition. These are basically the atmospheric properties that we measure, the things that are constantly changing and that together define our weather at any given moment and our climate over longer periods. The main elements are temperature, how hot or cold the air is, pressure, the weight of the air pressing down, winds the movement of air, humidity, the amount of water vapor in the air,
Right.
clouds, those visible masses of water droplets or ice crystals, and finally, precipitation, any form of water falling from clouds, like rain, snow, sleet, or hail.
Mhm.
Understanding atmospheric pressure differences, for instance, isn't just abstract. It's the fundamental reason why you feel a breeze on a summer day or why we experience powerful storms. It drives air movement.
So it's these 6 key ingredients: temperature, pressure, wind, humidity, clouds, precipitation, that are constantly interacting and shaping the atmospheric conditions we experience daily. And I guess changes in these elements are what we perceive as, different types of weather: sunny, rainy, windy.
Precisely. And the long-term averages and patterns of these elements in a specific region are what determine its climate. Is it typically hot and dry or cold and wet? These elements are definitely not static. They are continuously influenced by a multitude of factors: solar energy, Earth's rotation, geography, and they have a direct and significant impact on virtually all aspects of human life, from farming and transport to our health and well-being.
Okay, this has been a truly illuminating deep dive into something we, well, often take completely for granted: the air around us. So just to quickly recap, we've uncovered that the atmosphere is this complex mixture of gases, water vapor, and even tiny dust particles. Each component plays a critical role, from the greenhouse effect managed by carbon dioxide and water vapor to the essential UV protection from the ozone layer, and that surprising role of dust particles as the sieves for cloud formation.
Hmm.
We've also journeyed through the atmosphere's layered structure: the troposphere, the engine room of our weather; the stratosphere, protecting us with its ozone shield; and then the mesosphere, thermosphere with its auroras; and the exosphere, fading into space.
That's an excellent summary. It really highlights the intricate web of processes happening within this seemingly simple envelope of air above us.
So here's the final thought for you, our listener, to consider. Reflect for a moment on how the delicate equilibrium of these atmospheric components, even those that seem insignificant, like those tiny dust particles, profoundly shapes the world around us. From the very air we inhale every few seconds to the intricate dance of weather patterns we witness every day. It makes you wonder, what other unseen forces might be subtly influencing the complex systems of our planet in ways we are only just beginning to understand?